So, nochmal herzlich willkommen und einen schönen Nachmittag zu unserem Webinar mit Cyberdefense. Wir starten das Webinar jetzt. Es geht um den Schutz von kritischen Infrastrukturen, um den Schutz von Industrieproduktionsanlagen, SPSen. Und hierzu haben wir heute den Hajit Hoti als Sprecher gewonnen. Das Webinar wird in Englisch stattfinden. So, welcome to our webinar together with all Cyberdefense, and I will pass it over to Hajit. Hajit, maybe say a couple of words and then we can start with our webinar. Fragen bitte in den Chat. So questions please put in the chat.
Thanks, Richard. Apologies, I can't do the session in German. My German is a lot worse, so Richard can do both dialects, but unfortunately you'll have to listen to me in English. So yes, my name is Hajit Hoti. I'm the European Regional Technical Manager for OWL, and I've been working with the KO for a number of years now on our OWL data-diode products. Right, so let me kick off. I'm conscious of time. Sorry. Okay, so just quickly a little bit about OWL. OWL as an organization has been around about 20 years now. So the original idea started, I would say, late 90s, early sort of 2000, when the Russians and the Americans wanted to obviously decommission warheads. Obviously the Cold War was stopping and they wanted to exchange information. So that work was actually undertaken by one of the US military labs, and that's how the concept and the idea of the data diode happened. And that's when our original founder actually, got the idea and actually founded the data diode concept. So around 20 years or so, supply chain, everything is, and R&D is all based in the US. As you can tell, we've got a military heritage, but obviously that's been extended into the critical infrastructure space, which I'll talk to you about today. So obviously, everything built, all the manufacturing, R&D, all the software development, everything is done there. We've got 2,500 deployments. I would say it's probably closer to about 3,500 now when this slide, this slide was originally done. As I said, obviously DoD intelligence, the critical infrastructure, that's been going, I would say, for about, 12, 13 years or so. And now more recently, we're starting to see other use cases and really around companies having applications that are critical. It needs that additional security assurance, hardware assurance. That could be one way. It could be our cross-domain capability, which I'll obviously talk to you about later. So it's that capability to have that separation between these two networks, but obviously ensure the right data is going across, but obviously protecting those key assets on either side of the network. You'll see some of the technology. We've got a number of boxes depending on the use case, lots of patents. As far as certifications go, some of them are EAL certified, some of the cross-domain is SABI and below, or more recently that's called Raise the Bar. So again, I'll mention that as well. And obviously the third-party testing, our devices, our products are constantly pen tested, and obviously with some of the assurances I've mentioned, they do their own testing around that one-way nature and the actual assurance around the key platform. Two product lines. We sit in the, I would say, the commercial space, but with the cross-domain platform that I'm going to be talking about, what we've really done uniquely is taken that defense, military, that capability on the left-hand side and applied it to the industrial commercial space. Primarily, it's the same product, but obviously there are some specific variations to address, I would say, a more common use case, but obviously more focused on the critical infrastructure. I'll talk about that. So if you've probably come across one of our diodes before, the ones that you've probably seen are the two at the bottom. So we start off with a sort of, I would say, our entry level which is our DIN rail diode. Obviously DIN rail because of space. If you look at some of the industrial use cases, they don't have full server racks, they've got limited space, and obviously the throughput is typically a lot lower. So from this one, this is a DIN rail device. It's got independent data and management ports, which you can see there, but it runs the same operating system, which we call Talon, as the other devices. So it comes at a small form factor of 10 megabits, and it goes up to 104 megabits. So that, I would say, that's probably the entry level device that a lot of clients, when they're looking at a industrial use case like you guys are potentially at some of the small sites, it's a very good solution for that. Moving up to the left of that is the OPDS 1000. That's our workhorse product. I would say it's probably our most popular product. It's been around for a long time. It has up to a 1 gig throughput. It starts at the SC, which is 26. The MC is 155, and the HC is the 1 gig platform. It allows you to run all of our full range of connectors. Obviously, any of our diodes, you can run traffic simultaneously. And obviously, with most of the connectors, which I'll go later on in the present, we don't need these additional flanking servers. So it's that all in one box with all the proxies. And most of the sort of enterprise IT protocols can be sent through that device, simultaneously to multiple destinations. Cloud, enterprise, on-premise, it doesn't matter. They can accommodate all of that. So I would say that's your mid-range product. If you're going to want to go to the next range, then it's our server-based platforms. You can see a couple of Dell servers there. So typically when we do these, we tend to use Dell or HP servers. But, we could look at, and if you guys are partners and you want to build your own, you can do that. And what's actually inside of these are these V7 cards. So those are the cards that go from the 1 gig up to 10 gig. So there's one card in each server, so the send server, receive server, and there's a fiber cable in between. I'll actually show you that in one of the subsequent slides on the 1000, what the connectivity looks like. The benefit of using one of these systems is if you want to go 1 gig or higher, if you need more hardware resiliency that a server provides, and that you're thinking about entertaining, building your own system. So for those higher throughput use cases, it's a good one. We do have a system called Packet, which allows you to capture raw packets. And we have some use cases where people are taking, or customers are taking, a 10 gig span or a mirror tap or from an aggregation switch or something, and they want to feed those packets from a secure zone to a less secure zone, and they want to use something like an EPDS system or a passive system, which is a server-based system. So the focus of the presentation is around the IXD platform, and I'll give you the high-level highlights here. So it's a 1 gig or 10 gig system. It's called the Industrial Cross-Domain. So its heritage is from the ITAR or non-ITAR. It's a FMS product called the XD Guardian. It's actually the same hardware. So if you actually go onto our website and look at foreign military, it's that same hardware platform. It's the software stack that's slightly different. And why you would choose a cross-domain solution comparing to a traditional unidirectional really is the filtering capability. So if you're concerned about what's in the data, I want to control and filter that data either at an application or a protocol level, or actually what's inside the data itself. And that's really where the cross-domain comes into play. So if you look at our sort of defense military type of use cases, obviously they've been doing that for a number of years. What we've seen in the market, I would say for the last 2 to 3 years, and we have some specific customers driving that need, where they've got a lot of bi-directional applications, maybe coming from a smaller plant, going up into a main data center or a main plant. They need to feed that information. Some of it's one way, but a lot of it's two way. And they actually want to control, the type of data that's going from those zones. And it could be going from high to low, low to high, but I can't control all of that communication, one way. With the industrial cross-domain or these platform, these jumpers at the front, this is actually a 1 gig machine actually. But you can see these jumpers, depending on how they're wired up, and I have a picture of what it looks like inside, that will determine it's a 1-way or a 2-way flow. So that's the industrial cross-domain. I would say our initial feedback from the market has been very positive. And I'll go into some of the use cases, but I think what we'll start to find is from a wider industry, commercial perspective, where, companies or organizations have got key organizations and they need to protect these. This is where, the cross-domain and not necessarily just the diode will come into play, because this filtering capability is something people are used to in, firewalls and other things, but they don't have the diodes and they don't have the hardware separation and some of the enforcement that we talked about. So that's the key, or these are the platforms today. Obviously, if there's any questions on that, then please post them on chat, then I can take them away. So I'm going to quickly go into the more traditional products. That's the 100D, the 1000 and the EPDS. And these look the same from a perspective inside the hardware and the software stack. So with a diode, I would think of it as 2 independent compute platforms. You've got a send-only computer, you've got a receive-only compute platform, you've got a send-only diode, you've got a receive-only diode, and obviously, depending on which box it is, this is actually the 1000 actually, which they're showing here. There's a fiber that connects the 2 computers together, and the only way you can send data is across that fiber, connecting those 2 computers together. So that's how the concept of the air gap happens. We also have corresponding proxies, and those allow you to do the 3-way handshake, set up that TCP connection in the first place. Then what obviously gets pushed across the diode itself is that 1-way push, and that can be that 1-way protocol. It could be TCP or UDP, depends on the protocol. So in addition to the air gap, we have a protocol break. And so what do I mean by that? So the protocol break means when we actually send the data across the diode, we're not sending it in its original format. So just as an easy example, I'm going to pick something like mail SMTP. I set up my SMTP TCP connection. I send the data into the diode. That proxy will terminate the TCP connection. Then it'll also terminate and initiate that SMTP connection. So the mail message comes in, you'll get an application response back. The mail actually comes in, we actually send that mail message across the diode. But as we send it across the diode on the send only or transmit only diode, what we do is take that mail message, i.e. the application payload, we remove the layer 2 and layer 3 information, and we put it into an ATM envelope. So what we've done, we've taken the payload but put it into an ATM envelope. And the reason we use ATM is twofold actually. One, it's very reliable from a data delivery point of view, but B, from a latency point of view, it's very deterministic. It was extensively used, I would say 20 to 30 years ago in large telecom networks to deliver, data across these large infrastructures. So we actually send it in ATM. When it hits the other side, the receive only or the destination computer, we remove that ATM envelope and we put a new header, layer 2, layer 3 header, which is actually originating from the proxy on that destination side, and we send the packet further downstream. So there's an air gap, there's a protocol break. As I mentioned, I can send multiple applications simultaneously. They can go to different destinations, and depending on the protocol, and I'll cover the range, obviously, we sometimes have specific application connectors that are fully adverse for the underlying application, because that could be something like OPC, it could be a Modbus, it could be MQTT, it could be OSI soft replication. So there's a number of connectors that are natively built to sit on the diode itself. So I mentioned the optical air gap and the network segmentation, the proxies. Obviously, that gray box is the enclosure. The other key bit of a diode is the network confidentiality. Because we're using ATM and the protocol break, we are not transmitting any IP information across the diode. The actual routing or the mechanism that we send data is through ATM channels. And again, if you're familiar with the protocol, it uses this concept of channels. So what we do is actually map the channels to particular ports. So that's how the data is sent across and how we know which protocols and which ports to allow through. So that mapping of channels to ports, but that means there's no layer 3 information being sent across the diode. So because there's no layer 3 information, that there's complete network confidentiality on either side. So the source network has no knowledge of the destination network and vice versa. So obviously it's a closed system as far as that's concerned. And obviously because of the separation of the air gap, the two networks are separated. So that's the sort of basic principles of the diode. This is what it looks like inside. This is actually the OPDS 1000. So again, I mentioned the send server, that's the source computer, that's the destination. This is the orange cable I was talking about. That's the send only diode card. So that's the send only card. This is the receive only card, and data can only flow in that direction from the source to the destination. It's physically impossible to send data from the destination side to the send side. So hence, when I'm sending data through a diode, I can send the data out, but it's physically impossible to get data coming from your destination network back into the source. You can see the independent disks here, the solid state drives. These are my data ports at the top, and these are my management sorts. So typically on the 1000 and the DIN rail, these are copper ports. With the EPDS, obviously you've got slightly more flexibility. With the server-based system, especially if you're going 1 gig on 10 gig, then obviously they tend to have fiber ports as well. And on the the IXD, the 10 gig machine, again, those are SFP based as well. So depending, on what your media type is on your 10 gig network or 1 gig network. So this is the inside of the machine of the OPDS 1000. So just some quick takeaways. I mentioned the blind routing tables, network confidentiality. We only send the payload, no routing information, full role-based access control. And obviously I mentioned the two sides are completely isolated, 2 independent compute platforms, obviously separate fan power network. And normally the way the system is administered is done from a whitelisting point of view. So you say these IPs or this source or this network is allowed to use this port to send data. When it gets to the destination side, it's typically sent to one destination server. We can have sort of HA configurations on this platform and on the IXD as well. Separate admin ports, as I showed you, and effectively you've got that hardware separation between the two networks, the source and the destination network. It's actually driven by a menu-based system. You can obviously, because it's an underlying Unix operating system, but you shouldn't need to access that. But everything can be accessed via this menu-based system. But there's no GUI interface as such. So this is the sort of traditional unidirectional diodes. So that's the IXD. That's actually I think that's a 10 gig version, actually, if I'm not mistaken. So reason, market uptake, capability. So it's that real need to support those multiple industrial protocols. Typically they're one-way or two-way. Obviously, it's critical data uptime is key. Throughput, so 1 gig, 10 gig is obviously common because of the nature of where it's located and the type of data going through. And if you compare it probably to our more traditional solutions where we had a one-way and a two-way diode, obviously this allows you to reduce the number of machines. Since we don't use any flanking servers, then you've got the all-in-one box, but obviously you've got the higher throughput in that sort of one new appliance form factor. And as I said, the real need for the CDS, the cross-domain capability, is actually to look inside the data. So this is the protocol doing what it should be, what's inside the data, you know, the type of data going through, is it what expected? Can I do further filtering of the policy, you know, between those, the data going between those two key networks? And again, this is taking our heritage, our experience, you know, in the defense, military use case and applying it to the industrial use case, you know, with the same underlying technology, but bringing our traditional focus on critical infrastructure and overlaying things like the protocol adapters and some of that experience that we had for a number of years in that. So when I mean government tested and accredited, as I said, it's based on the same family as the XD Guardian. So if you go to the website and actually have a look, you'll look at that. That's a, you know, that can be exported, that product. And it's typically one of the foreign military use cases is the Joint Striker Force, F-35 airplane or aircraft, and it's deployed to get data from that particular device. But so from a hardware perspective, it's the same underlying hardware, but it's the software stack, and which we call the trusted software component, that's different. And the main differences are that it's around the multiple simultaneous one-way and bidirectional flows. Obviously the FMS use case, you know, it doesn't support things like Oracle synchronization, it doesn't support Pi replication and stuff like that. So what we're doing is building and having the knowledge of those protocol adapters that we've used in our traditional diodes and actually moving them to this platform. But the underlying hardware, the operating system, which is what we call the trusted OS, is fundamentally the same. It's the software stack, the trusted software that's different. And as I said, it's filtering and restricting the data transfer from those two domains. High availability, and again, due to where these devices are being placed, high availability is key. So it's typically deployed in a sort of primary, you know, active standby type of mode, but they're both in line. And when the primary one's not available, the secondary one kicks in. And as I said, it's a one new rack appliance. So from the government certification, the core platform has gone through SABI. SABI, the newest iteration, have raised the bar. As I said, the difference between the XD Guardian and the IXD is the software stack. On the US government side, to do that certification, it normally takes about a year. So it's quite an extensive certification. So the plan is to go through and actually get the IXD certified, but obviously that's just getting into a lab, having a sponsor and all that good stuff. And that does take a little bit of time. But as I said, the core platform, the hardware certainly has gone through that extensive government certification and accreditation. So probably just repeating a little bit what I said. So with the CDS, as I said, it's two independent compute platforms, two diodes, two completely independent paths, obviously with a fiber connection in between. But the key thing is it's that data flow restriction and the content inspection, the filtering on. And again, just adding to what we said about the diodes, where we had the ATM protocol break with the IXD, it's the same thing. We're actually transforming the data typically into XML. And what's actually going across the diode is the XML, you know, conversion. So it's the XML representation of that original metadata. So when we're enforcing policies, it's doing known good. So we only allow known good data, across the device. Obviously, all in one. Depending on the type of protocol, so things like FTP, SFTP, Pi, and things like that, we reach out, get the data and push it across, and then actually push it out to the destination servers. So again, you're getting a CDS defense grade security technology, but obviously applied to the industrial use case. So here's a sort of high level, I would say, a functional representation. So you've got the IXD. I mentioned the protocol adapter. So this is the raw adapter that understands the application. So obviously for Pi, it will understand the Pi protocol. For DB synchronization, that's actually Oracle. That will understand TNS, which is the native Oracle protocol. Same with syslog or TCP or UDP. So there's the native protocols that we've written that understand the actual application. And what that does in the next layer, it'll actually do the XML filtering. So that's when we convert that metadata into XML. Then we have the various pipelines that do the additional filtering if needed to be. So, and again, that depends on, what level of filtering, what needs to be done. And again, as I said, across the diode, it's that XML representation that's going through. So it's actually XML data that's typically sent across. And again, on the other side, we transform it back. It's gone in, sorry, you see XML, then it's transformed back into the original protocol and sent out. So the benefit of the IXD is you can have bi-directional flows in either direction. If you look at the filtering, they're completely independent filters. So for example, if I'm doing databases, I could be querying a database, inserting at the other side, or just simply doing an insert from one database to another. But I could be restricting the type of data I'm inserting. I could also say I can't do any DDL, I can't change the structure, I can't drop any tables. So with filtering, you can be obviously more granular, more specific on the type of data going across those two domains. And those filters are typically different in each direction. So for the database, if you're selecting data, you might say, I can actually, run a query on a particular table, but the results that get sent back, I could restrict the type of data, how much data I send back and stuff like that. So it's having that, that independent sort of pipeline that does that. The sort of combination, mixture, sizing from protocol adapters to pipeline depends on the applications, the messages, and the throughput. So we have quite a lot of flexibility of how we, map pipelines to adapters, and again, we'll work with you to actually size it depending on the throughput and the performance that you need for some of those applications on the left-hand side. So this was actually a large deployment that we've done. And again, those were the applications that they wanted to push across, those sort of 5 or 6. Remember, these are going across simultaneously. And this was, they deployed this on a 1 gig and a 10 gig system. I mentioned some of this, so multiple protocol support, one-way, two-way communication. I'll show you a couple of screenshots, but we have a configuration manager that allows you to do this. This is a completely stateless, headless system. So that means there's no access to the device. We use SE Linux policies. We have a trusted operating system, and I'll go into that in a subsequent slide. But so basically all the logging, all the performance is either outputted through SNMP or syslog. And again, we have the data and the management ports. So there's no there's no physical access to the device once it's running. Once you put those rugged keys, like the sort of rugged USB, once they're actually in, they can be left in as the system powers up, but they can be taken out. But once that's in, the actual TOS and the TSE is loaded onto memory, so there's no physical access to the machine. And obviously, if someone tries to manipulate or change something, then the system stops functioning. So basically, there's no way to interact with the system apart from using the SNMP or the syslog to see what's going on and how it's been performing. All the configuration is done through that configuration workstation, either through a sort of Unix-based command system or through that GUI application. Those are some of the protocols we've got today. We've obviously got a lot of that are coming up as well. You can support and write your own adapters using the more general UDP and TCP ones. So again, we can show you, advise you how to do that as well. And obviously on the right-hand side, there's more finer filtering capability as well, if you need to do that. With things like files, we can look for particular file extensions and file types, and that can be blocked as it's sent across as well. I'll go into some of that, the other stuff, but the trusted hardware and the trusted OS, obviously that's a key, sort of using those foundations to have that key hardware or that, secure hardware, then build it all up to the software stack. And remember, the trusted hardware and the trusted OS, that's the one that's been, SABI and RTB certified. This is one of the use cases, similar to the other slide I showed you, but they were doing HTTPS, SFTP, PI replication, and database replication. So again, it was those 4 flows in parallel. I think this was a 1 gig and a 10 gig system, actually, both in a HA cluster. And again, due to where these devices being placed, we generally find HA is an important concept because of the data going through these devices. So typically it is set up in a HA pair, but obviously it can be done in isolation as one device. The second use case this particular client had was ICCP transfer. So ICCP is a protocol used to send information about consumption, data being generated, by that power provider. It can be used to send to an authority or the local regulator. And what they were doing was actually using that to send their ICCP data, ICCP transfer to that third party, and actually getting data from them. So it was a effective external connection to a number of third parties, but they were using the IXD to separate that. So in this case, as you can see, it was 2 different sites, but they had their own infrastructure controlling, how the data got sent out. So this was an ICCP use case. The other was a more broader use case where it was more in the sort of core of the network, separating. I think it was sort of between data centers. You can't really see the zero trust defense. So the data keys, as I mentioned, so what you do, you build the config. The hardware has its own hardware or encryption keys, and you sign your trusted OS and your trusted software component, and that's all generated on your workstation. With those keys, you build your config, you transfer it onto those data keys, and then you can boot the system up. And as I said, you can take them out. Obviously, if the system comes back up and the keys are not in there, then it won't start because it doesn't have a known good state. So we're using mandatory access controls and discretionary controls. So the mandatory access controls are enforced by SE Linux. we obviously are doing the file and integrity system checking. That's how we know if the system has changed. Then obviously it stops and it stops passing traffic. As I mentioned, it's a stateless, headless system. There's no access to the device once it's operating. So there's no local remote user accounts that you can do it. And that, once the state is in memory, that obviously is the known or the last good operating state. So stateless operation. And obviously the key thing is, you know, you're passing the data, but you're checking and validating the data. All the logging, as I said, it's done through, typically most clients do it through the management port, and they'll have a syslog or a SNMP manager. And this could be, you know, we've used things like Zabbix for SNMP. On the syslog side, you could use your standard enterprise SEIM. So it could go to a logarithm, you know, ArcSight, it could go to a Splunk, you know, the sort of standard industrial, you know, sort of enterprise ones, or it can go to a local based system as well. I would say, I mean, it's an interesting quote for NIST. You know, these CDSs, it's really, you know, competing with, I wouldn't say the sort of industrial firewalls, it's really your enterprise, you know, your top tier firewalls where they do have some filtering, but obviously they don't have the hardware enforcement. They're not doing the protocol transformation and the protocol break. So, you know, it's that hardware separation between the two zones, and that's really where it's coming into play. And obviously this has been done in the defense military use cases for a number of years. So I mentioned this, the trusted hardware component. So we have the two independent transceivers, and basically those jumpers will determine which way, but you can't, you know, obviously swap them the other way around. So the hardware is enforcing those. We have those, you know, those specific transmitters or transceivers that do that. So the actual underlying hardware is obviously purpose built. That's actually the 10 gig system that you can see there. And if I hover my mouse, that's the, you know, the rugged key or the data key that I was talking about. So that's where, when you change the configuration, you obviously put it onto your data key, then that's uploaded back onto the device. So just from I mentioned there's two independent compute platforms. Obviously, those jumpers at the front will determine whether it's one way and two way. We have a customer already that wanted a CDS. They wanted it as a one-way device. So again, that is possible. And again, you know, that's something we'll see more and more of, that, you know, where they actually want, you know, a CDS capability, but they just want to be able to take data in one direction only, as you have, you know, with the traditional device. So each side is only able to transit or receive data, and those jumpers at the front determine which direction they go to. So it's a complete compute platform with the motherboard and the ICE communication cards, and that's actually, you can tell from the jumpers, that's actually the 1 gig system. So that's the trusted hardware component. Remember, this has been certified, US government certified. This is the trusted operating system. We actually use Red Hat 7.7. So it's obviously a very cut down system, and we use the mandatory access control of Red Hat, and we obviously use SE Linux. So our Traces, our sort of one of our sort of companies that we merged with a few years ago, they've got extensive experience with SE Linux, building SE electronics, and we also have courses on that. So what we've done is taken that sort of rich pedigree we have and actually hardening that underlying device. So what we're really doing with the SE Linux policies is ensuring our software processes are tied totally tied down, so there's no way to manipulate some of those core operating system processes. So basically that ensures there's only the required functionality needed to ensure the IXD actually operates. Here's the trusted software component. So this is the layer on top that does the filtering and has the protocol adapters and stuff like that. As I said, the TSC is cryptographically bound to the hardware and the TOS. So that's where you've got those keys, and the TSC is actually loaded, from those data key rugged drives during the startup. So they can be taken out once the system started, but obviously if they're not in there and if there's a power failure, then obviously it won't come up. And as I said, the relationship between protocols and adapters, it depends on the number, how much throughput of application messages, the type of filtering and everything else going on. So that's something we would work with you to size the device, how it should be. And again, this is 1 gig and 10 gig system, and you can see that's the 1 gig system. This is the linear pipeline. Again, these are the filters I was talking about. What we're doing is normalizing that data into XML, then we apply the schemas, and each of the outcome of that. So as it goes through the various steps, it goes into, from the protocol adapter, converts it, then goes through the various filters like the XLLT or the XSD or the XProc. Each stage of that filtering process is actually outputted to syslog. So that's how you can tell if something has been rejected or hasn't gone through, because obviously it's not known good or it's not applied according to the policy. So that's the filter. That could be the filter. That's actually a UDP filter, but obviously you have TCP. You could have an independent, a completely different filter, on the return path. If you're going from high to low, but there's an acknowledgement coming back, then that filter in the other direction, is completely independent. And typically it is very different. This was the configuration manager that I mentioned. So that configures the TSC. It also signs the packages that goes onto the TSC. So it's cryptographically signed. So that the TOS and the TSC are signed by the same packages, by the same keys. And so to run this configuration manager, that runs on a Linux platform. So this is the GUI version, but you can obviously you can do everything through the sort of raw files if you want to. So with configuration, all the IXD configuration is done off box. You take it off the box, you apply, sign those packages, then put it onto those data keys. Here's a basic example. You can see you've got the mode, whether you want HA, NAT, and some basic information about IP. So this is where you go into the protocol adapters and the pipeline. So with the protocol adapters, it will give you a list of adapters that, in the IXD TSC, and then you can choose, and this is how you can map the pipelines and stuff like that. So most of the configuration can be done through this GUI interface. So that's this sort of core of the IXD. We've seen this before, I suppose, in parallel to the CDS. What we're doing is the next generation of FPGA products. Our next generation of data diode products, which will be based on the IXD software and the operating systems, but underpinning that will be some of these FPGA products. So we have a few. Radium is the UDP one that goes 1 gig. The Cobalt can do TCP and UDP. It's got a small processor to do the TCP and any specific filtering. Obviously, it's got the FPGA as well. And the Titanium is the higher throughput 40 gig FPGA. So different products for different use cases. Yeah. So this is I would say, an older slide focused on some of our older guides, but the ones in red are typically that come in the key operating system. As you know, what we're doing is taking some of these connectors, moving them to the IXD platform. So things like the Pi connector, that's being transferred, and obviously we'll start to work on some of the others as well, things like OPC, Modbus, and some of that good stuff. High level use case, I would say for our more industrial use cases, and again, the IXD is a prime example where we could be sending data outside. It could be to the cloud, or it could be, to another location or something, or we've got third-party connections coming in. We've got one-way, two-way. We might have a tier of firewalls on the north side, then we're controlling, through that hardware separation on the IXD, the data going out. But again, there's a number of connections here, one-way, two-way. You might want the HA, and obviously you've got a number of destinations here. So this is a really good slide that shows you some of the, data types, some of the providers we work with. So you can see some of the large OEMs. You can see OSIsoft, the Historian, the Aviva one. You can see some of the cloud providers. We've done a lot of work with Azure IoT, AWS, obviously some of the other SEMs as well. So with things like Splunk, we can do the standard syslog on the files, but we can sit, between the Splunk components. We support the Splunk Connect for syslog as well. So there's a number of integrations done with some of these, I would say, more bigger enterprise platforms, how we say it. But I suppose the point is, you've got inputs, you've got different destinations. In theory, having the diode or the IXD allows you to connect with the diode, like a 1000 on the EPDS, allows you to get the data out, do this simultaneously, have these multiple connections. With the IXD, you might have connections coming back in. So you're vetting that data, one-way, two-way flows, and those could be, connect to a number of third parties as well. And again, this could be a HA configuration where you've got two devices sitting in parallel to each other. So I would say this slide probably covers a combination of a lot of our more standard use cases. I would say on the industrial side, cloud connectivity is a very big one that we're seeing, and we'll start to, we'll continue to see more and more of that as clients are sending data to the cloud. Here's our Pi use case. And again, this is taking Pi from the OT side. We have a Pi connector that uses one of their APIs. We interact with the Pi system using Pi Trust, take that data, then push it to the replicated Pi system on the IT side. Our OPC, Modbus, and stuff like that, those other connectors do a similar thing as well, where we're taking data from the source system, typically on the OT side, and pushing it to the IT side. And with Pi and things like that you have instances in the cloud, so they can send that data to the cloud as well. Here's an interesting use case around the CyberVault. We work with one particular manufacturer, Dell primarily, where they've got their data center, they've got their CyberVault. What we're doing is taking the monitoring data out the vault with the One U appliance. It's taking typically monitoring, reporting data, mail, syslog, and SNMP. And if you want to send secure updates back, then we have this SAS or a 1000 box, which is pushing that back through. And again, this is a very big use case, a more commercial use case where it's been sold to, hospitals, schools, large, very commercial organizations outside the more traditional sort of CI use case. And here's the cloud use case where I said you want to get data out your OT network. You want to protect that asset from, from the external, i.e. typically the cloud or the internet, but you want to get the data to the cloud. And this is a prime example of a very good use case where we can get that data out. And here's a sort of use case around MQTT where we're sending data to IoT Hub. Right, guys, I'm conscious of time. Wanted to make sure I left some questions. I think, Richard, I don't know if there's anything on the chat.
A couple of questions in the chat. The first one is there a speed maximum for the optical air gap?
For the IXD, obviously, because it's a 10 gig machine, or the diodes are 10 gig, it's 10 gig. With the smaller diodes, yeah, we do it via software. We can control the data going through the air gap. Yes, yeah. But depending on which card, for the 1000, the maximum is 1 gig. Obviously, we can tune it down depending on the rate key. But on the IXD, it's 1 gig or 10 gig. So those ICE cards I was talking about, they operate at 10 gig, and you can have a 1 gig or a 10 gig version. But there's no metering or control of data on the IXD. You get the full throughput, either 1 gig or 10 gig.
Okay. The next question, a very political question. Is the data diode replacing industrial firewalls that are rail mounted and designed to manage industrial protocols, or is it an add-on?
I would say it's both, actually. It depends. In some cases we are. The management of firewalls is obviously quite extensive, the patching and everything else. I would say for smaller sites it is. We are, like the 100D, maybe the FPGA diodes going forward will replace, the FPGA diodes are intended to potentially sit on a, like a wind turbine on an oil rig or something where you're protecting one asset. So yes, that will be replacing an industrial firewall. If you look at the IXD in its current state, no, that's a much more high-end security device. Is typically complementary to your firewall pair, connecting you to the internet, but it's protecting that those key assets or that critical infrastructure. So I would say IXDs, no, not even in the same space as the industrial firewall. The smaller diodes, yes.
Okay, thank you, Harjit. Maybe to add on this, that I think that the industrial firewalls, they're more, they're broader, more, but and the diodes, they help you to segment a special field, which is really needs to be secured. And I think the big advantage of a diode is you never need software updates, you never need any patching and everything. So it's there and they run for years without anything. So I think this is a big advantage.
Yeah, I mean, with any firewall, it's all down to the configuration, right? If the configuration, the patching, that's key. You need to keep on top of that. If you don't do that, then obviously there's you're susceptible to a compromise. With a diode, you can't. Obviously, you may be able to compromise the destination side of the diode, but you still can't get through to the source. That's just impossible. So you've always protecting that critical asset on the source side.
Okay. Next question. Can the management of the data diodes be centralized in case of more than one location? That's a tricky one.
I would say with the standard diodes, we can't do management, we can do monitoring. With any of the systems, you can do it with, syslog, so you can monitor the actual functionality, the capability of the diode. With the IXD, you can. If you look at the large defense type of projects where they have a I'm talking about the Joint Strike Force, the JSF, they may have a number of IX or XD Guardian machines, they would be done through a central management station. So yes, with the IXD, yes. We are building that more enterprise type of management tier as well, but yes, with the IXD, yes, definitely.
Okay, and especially for the small diodes, you have even, as you mentioned before, 2 management boards. So one is managed maybe from the OT side, and the other one is managed from the IT side, so that there's no interference between IT and OT. So that's
exactly. And you can take configuration, on the smaller diodes, you can take it, apply it to other diodes. So you almost have a set configuration. You change your IPs and you're ready to go. So you don't have to configure every device from scratch. We have clients that do that. They have a sort of template configuration they apply to any new device, and they just change the IPs and they're ready to go.
Yeah, and especially it's the nature of the one-way diodes that
exactly.
You can't get from outside into the inner side of the diode. So even for management, you can't get in because
exactly.
It's physically impossible.
Exactly. So you've got two independent compute platforms, right? So you have to manage and build a system independently on each side. So that's the whole point.
Okay, I think at the moment we are done with all questions. I would say thank you for everybody. It's quite a big audience who was here again, and thank you, Harshit, and I wish everybody a nice evening or a nice afternoon. Thank you very much.
Thank you, guys. Thank you for your time. Thank you, Richard.
Okay.
Guys.
Einen schönen Nachmittag und bei Fragen bitte bei uns melden. Vielen Dank. Tschüss.